Good morning, everybody. So today I'd like to talk about the Diels Alder reaction, which is something that's happening in the lecture right now. Okay, so let me talk for about 10 minutes, maybe just to lay out the most important features of the Diels Alder reaction, and then we can do problems. Diels Alder. Okay, so let's first of all talk about the overall reaction. RxN means reaction. So the Diels Alder reaction involves two components. The first component is called the diene, and this has to be a conjugated diene, where the two double bonds of the diene are separated by one single bond. Okay, so this is the diene, and I don't want to get into this right now. I'll get into this a little bit later. But the diene usually will have electron donating groups. So usually has electron donating groups, which takes an awful long time to say it, right? So I'm just going to say EDG, electron donating groups. All right, and so what are some examples of electron donating groups? The diene might be bonded to an oxygen atom that can donate its electrons by resonance to the double bonds of the diene. Another very common electron donating group that we see on the diene is where the diene system is bonded to a nitrogen atom. And once again, this nitrogen atom has unshared electron pair that it can kick into the diene. So that's an electron donating group. Another electron donating group that we see here could be alkyl. And this is not electron donating by resonance, but rather by induction, because the sp this can donate electrons. We've seen this effect several times before. For example, we know that a tertiary carbocation is more stabilized than a primary carbocation. Why? Because the tertiary carbocation has electron donating alkyl groups. We've seen that the tri-substituted alkene is more stabilized than a monosubstituted alkene. Why? Because that alkene has electron donating alkyl groups. Okay, so that's the diene. Next component is called the dienophile. And the dienophile, in its simplest manifestation, is just going to be an alkene. This is the dienophile. And I don't want to get into this too much detail right now. I'll get into it later. But the dienophile, this will usually have electron withdrawing groups, right? And electron withdrawing groups, that takes an awful long time to say it, right? So I'm just going to abbreviate it, EWG. And what are some concrete examples of electron withdrawing groups? Most important one that we see a lot would be the carbonyl group. So there's going to be a carbonyl group, either of a ketone or an ester or something like that, on the dienophile. Another concrete example of an electron withdrawing group that we see on the dienophile will be the nitrile functionality. Okay, and both of these are electron withdrawing by resonance. So we'll see these groups tacked onto this dienophile many times. Okay, so now the reaction is heated, and the mechanism of the reaction involves the movement of all of these double bonds to create new double bonds and to create a ring. So these electrons come in here, these electrons go down here, these electrons come down there, and the product of the most primitive kind of Diels Alder reaction is this cyclohexene ring. Okay, notice is that we have a new double bond. I'm going to put a little star there and a little star there. These two carbons that used to be bonded by a single bond in the diene are now tied together by a double bond in the dienophile. And notice that in the product. And notice that the two carbons that used to be bonded together by a double bond in the dienophile, they end up bonded to a single bond. And that new single bond is diametrically opposed to the location of the new double bond in the cyclohexene product. Okay, so that's the overall reaction. Diene plus dienophile, you get a cyclohexene ring. The dienophile is not limited to an alkene. So sometimes, I'm just going to put it here rather than erasing everything, sometimes the dienophile can be an alkyne. So sometimes the dienophile can be an alkyne. There's the diene. There's the dienophile. This time it's an alkyne. Shoot this thing, and the electron circulation is the same. Once again, this is a way of making a six-membered ring. The two atoms in the diene that used to be bonded by a single bond are now bonded together by a double bond. And this triple bond of the alkyne dienophile is degraded to a double bond. So here are the two carbons of the alkyne dienophile. They now become these alkene carbons. So when the dienophile is an alkyne, the product is going to be a cyclohexadiene with the two double bonds diametrically opposed to each other in the product. Okay, so that's the overall Diels Alder reaction. It's a way of making a six-membered ring, a cyclohexene or a cyclohexadiene, depending on what the dienophile is. Okay. Next, let's talk about regioselectivity. Regioselectivity. Okay, so here's our there's the diene, and now I'm going to put an electron withdrawing, I'm going to put an electron donating group on the diene. So one of the electron donating groups that we talked about would be the, for example, the methoxy group, right? This is electron donating. This oxygen has unshared pair of electrons. It can kick them into the diene by resonance. Okay, now let's look at the dienophile. And this time I'm going to put an electron withdrawing group on the dienophile, which is usually what we get. It's usually the situation. So I'm going to put this carbonyl group on there. Okay, heat this, and we get motion of electrons. We're going to get a new cyclohexene ring. where the single bond of the diene is now a double bond in the product. The double bond of the dienophile has been degraded to a single bond. Okay, and so now this guy, the way I've drawn it here, could be here, would be there, and this guy would be there. Okay, but what we have to consider is that this is not the only orientation that can be adopted by the dienophile, because I can draw the very same diene, but this time what I'm going to do is I'm going to flip the dienophile into an opposite orientation so that it looks like that. Right, it's the same molecule, it's just kind of like the oxygen pointing up here, the oxygen pointing down here. All right, and so once again, the motion of the electrons heat this thing. Once again, you're going to get a cyclohexene, all of that blah, blah, blah that we talked about before. And now the methoxy group is going to be down here, and the electron withdrawing group is going to be down there. Okay, so these two guys are regioisomers. They are constitutional isomers. They are not the same compound. And we have a rule for predicting the orientation of electron withdrawing group and electron donating group in the Diels Alder reaction. And that is that the electron donating group and the electron withdrawing group in the product prefer to be either 1, 2, or 1, 4, but never 1, 3. So this guy here, that's the electron donating group of the diene. This guy here, that's the electron withdrawing group of the dienophile. So the preference is for the product to have a 1, 2, or 1, 4 orientation of these two pre-existing groups. This guy has a 1, 3 orientation. That product is not observed. This guy has a 1, 2 orientation. What are we counting? We're counting the location of the electron donating group and the location of the electron withdrawing group in the product, and we are numbering the carbons in the new cyclohexene ring. So this is the 1, 2 orientation. So that would be the product. So this is the issue of regioselectivity. This dienophile can orient itself 2 ways, but the preferred orientation produces either the 1, 2 or the 1, 4 orientation of the electron donating group and the electron withdrawing group. So we're calling this, I call this 1, 2, but this is also called ortho-like. Don't like that term. So did you get that? 1, 2 or 1, 4? How about let's do a problem? There's the diene. It has that electron donating group on it. Here's the dienophile. Heat, draw the structure of the product. So I'll give you a few minutes to cogitate on that. All right, so we're going to get the cyclohexene with the methoxy group here, and the way I've drawn it the electron donating group of the diene and the electron withdrawing group of the dienophile in this orientation worked out 1, 3. No good, right? Because the electron donating group and the electron withdrawing group should come out either 1, 2, or 1, 4. All right, so how about we imagine taking this dienophile and this time flipping it. Heat. And so the way I've drawn it here, we see that the pre-existing electron withdrawing group and the pre-existing electron donating group with this orientation come out 1, 4. So that would be the observed product. That's what we would predict as the observed product. So there's an issue of how the dienophile, this guy, the alkene, orients itself relative to the diene. Okay, so that's regioselectivity. This guy, this 1,4 orientation, I call it 1,4. What are you numbering? The carbons in the new cyclohexene ring of the product. But this is also called para or para-like. So if you look at your lecture notes that Professor Porco gave you, and maybe if you look in a book or online, they're talking about ortho and para. Don't like those terms. I like 1, 2, and 1, 4. All right, so that's regioselectivity. Okay, now, next issue to talk about with Diels Alder. Oh, this chalk is killing me. Okay, next issue to talk about is stereochemistry. All right, and this is a lot more complicated than regiochemistry because this involves visualization. It also involves artistic skill. So how we usually describe the stereochemical outcome of Diels Alder is we talk about the endo group. Okay, and so in a sentence, what we're looking for here is that the electron withdrawing group, and where is the electron withdrawing group? On the dienophile. The electron withdrawing group is tucked under the diene. Okay, and so this is one way of being able to predict the stereochemical outcome of Diels Alder. Okay, so let's look at something. Let's do a problem that we did before. I think we were looking at this. Right, so this was a system that we just talked about, and we went through the regiochemistry. We saw how this is going to give a 1, 2. I better draw this in the way that makes that 1, 2 product a little bit more obvious. Okay, so now, stereochemistry. The product that we're going to get is this. Right, we just went through all of that about how this gives that 1, 2 relationship of the pre-existing EWG and the pre-existing EDG. But here we've created a chirality center. Here we've created a chirality center. And so both of these bonds here, which I haven't illustrated with any dashing or wedging, could be dashed and wedged. So we want to figure out how are they dashed and wedged relative to each other, right? I'm not talking about absolute configuration. I'm not talking about a way to predict whether this is going to be R or S. I'm talking about the relative orientation of these two bonds. Okay, so this is how I do it. You can do it any way you want, but this is how I do it. Here's the diene. There's the diene. Okay, all I've done is I've taken this diene, which was like up and down, and now I have flattened it out, right? We see that the double bonds of the diene must adopt this C-shaped looking thing, right? This is called the S-cis conformation. This is the only way this reaction can work is if the double bonds of the diene form a C-looking thing like this, right? A C. Now I'm going to get the dienophile into the act, but I'm going to tuck the electron withdrawing group of the dienophile under the diene. So that would mean, and I'm going to tuck it under in a way that I'm going to get that 1-2 1-2 regiochemistry, right? So there's a hydrogen there, there's a hydrogen there, there's a hydrogen there, there's a hydrogen there, and I'm tucking the dienophile under. So this might be, so let me illustrate here, right? There's the C shape, there's the C shape of the diene. Here's the dienophile. The dienophile is tucked under. Not like this, right? Not like this, but like this. There's the C of the diene. Here's the dienophile tucked under. Not like that. That's not tucked under. Like this, tucked under. Okay, so now, when we heat this, okay, so there's a hydrogen here, right? Can't forget about him. There's a hydrogen here. Can't forget about them. So I get, here's the single bond that separates the two double bonds of the diene. This becomes my new double bond. Okay, so there's my cyclohexene. But this guy here, this is called acetyl. That's the electron withdrawing group. He was in the back. He got tucked under so that in the product, the electron withdrawing group is going to be back here somewhere. You see how that guy is in the back? You see how that's the result of being tucked under? There's a hydrogen here. There's a hydrogen here. Can't forget about him. This hydrogen didn't get tucked under. He's going to be in the front. I'm going to draw him on a wedge just to emphasize that he's in the front, whereas that acetyl group, that C double bond O methyl group, they're in the back somewhere. Okay, so there are two hydrogens here. One is on the dash, one is on the wedge. Doesn't really matter. Just draw them anyway. Okay, and now this carbon up here where the electron donating group was, this hydrogen is closer to us, right? Because the diene got tucked under and this hydrogen is closer to us. So he would be on a wedge. And this methoxy group, he's going to be on a dash. He's going to be back here. Because remember when we draw an sp3 hybridized carbon and trying to draw dashing and wedging, we have two solid lines, we have a dash and a wedge. So I hope you can understand this drawing. There are other ways of drawing it. This is how I do it. I'll show you another way in a minute. Okay, so that would be the structure of the product with its stereochemistry drawn. All right, so how about let's straighten this up. If I were taking an exam, how would I want to present this? Pre-existing electron withdrawing group of the diene-O-file is in the back. I'm going to show that on a dash. Pre-existing electron donating group of the diene also on a dash. So sorry, everything got kind of crowded here, but I have to. So this is the relative stereochemistry. You see how they both came out on dashes. That doesn't always happen, but that happened in this case. But this diene-O-file, right? The diene is a little C. Here I tucked the diene-O-file this way, but I could also have tucked it up here on top. So the point I'm trying to make here is that this guy is actually the semen, right? You get two enantiomers. One of them has two dashes here. The other one has two wedges there, right? So it just depends on how you tuck. All right, so that is the endo rule. You're tucking under. Okay, let's try another one. So again, revisiting a problem that we did earlier. I'm going to imagine this, I'm going to try to draw this another way. This takes a lot more artistry on your part. Maybe you won't like it as much. There's a tabletop. That's where the diene is sitting. That's where the diene is sitting. I'm going to put an electron donating group here, methoxy. Okay, so there's the diene sitting on my on a tabletop. It's plain. Here's another tabletop. Oh, but this tabletop see how it's tucked under? This will be the tabletop of the diene-O-file. See how I tucked the tabletop of the diene-O-file underneath the tabletop of the diene? What would have been wrong? Something like this. Like something like this. That's not tucked under. Okay, so now I'm going to put the diene on this tabletop, but I'm going to put my electron withdrawing group, which in this case will be Cn. I'm going to put him so that he is tucked under, right? So it's this is wrong. That's wrong, right? That's not tucked under. That's tucked under. Okay, and so this is the orientation that these two molecules, which these two molecules must approach each other. Heat, I'm going to get there's my cyclohexene ring. with the electron withdrawing group of the dienophile is in the back there as a result of the tucking under, and the methoxy group would be here. Okay, so that's another way of representing the stereochemistry. How about let's straighten this out. It's 1, 4, 1, 2, 3, 4, and this is in the back here. That's in the back there. It's supposed to say CN. Barely. And it's on a dash. And once again, that's a new chirality center. And you're going to get a racemic mixture. Some are going to be 50% of the time that's going to be on a dash, 50% of the time it's going to be on a wedge. So this example isn't quite as instructive as the one we did earlier because this doesn't show the relative stereochemistry between two groups. Okay. How about let's do some problems? How would you synthesize that molecule using a Diels Alder reaction? So let's see if we can come up with what plus what are going to give that molecule as a result of a Diels Alder reaction. So there's a cyclohexene ring. That's the ring that was created by the Diels Alder reaction. There's the double bond in the 6-membered ring. This used to be a single bond, and it used to be flanked by 2 double bonds. So this guy would be made by reacting this thing, right? That's this part. And on the 6-membered ring, diametrically opposed to the new double bond, this used to be the double bond of the dienophile. So that plus that makes this. Yes? And notice that these 2 hydrogens are both on wedges. This molecule, this is showing their relative stereochemistry. This guy got tucked under, and so that's why these 2 are on wedges. Okay, so let's try another one. Put the double bond there, and maybe put ethoxycarbonyl up here, and ethoxycarbonyl down there. And notice these epoxy carbonyl groups here, they're trans. One is pointing up, one is pointing down. Well, how would we make that by a Diels Alder reaction? Okay, so up here, these two guys were these two guys were these. They got together to form that new six-member ring. And so here's the double bond that was between those two stars. That used to be a single bond. That's the electron withdrawing group. That's the electron withdrawing group. The dienophile double bond was here, right? Because the dienophile usually has a electron withdrawing group on. So there were my dots. Okay, this used to be on either side of these stars. These used to be double bonds. And the dots that used to be, whoops. Double bond there, double bond there. And these dots, there used to be a double bond in between here. Okay, but notice that I have this trans stereochemistry of the product. That means I had to have that trans stereochemistry in the diene file as well. Okay, so there's my combination of diene and dienophile. Okay, so this guy doesn't, I don't need to clean him up any, because he's presented in a sort of a standard way. But this guy, if I wanted to draw this in a prettier way, it would be that. The six-membered ring with two double bonds in it. Yes, so you're getting the hang of it? Okay, so how about let's try some product prediction. Okay, so see if you can come up with the product of this Diels Alder reaction. And I would need to see dashing and wedging. Did you find the diene? Did you find the dienophile? Okay, so here's the diene. See these two double bonds here, that's the dienophile, but we made the point that the double bonds of the diene must adopt the S-cis conformation. It has to look like a C. This does not look like a C. So what we need to imagine is rotating this bond. So that what we're looking at is really something that looks like this. Yeah, so here we have that C looking shape that we need for the Diels Alder. Okay, and so now what I'm going to do is I'm going to try to picture the diene and the dienophile approaching each other. And remember, the electron withdrawing group of the dienophile has to be tucked under the diene, and the electron donating group of the diene has to come out 1, 2, or 1, 4 vis-a-vis the electron withdrawing group of the dienophile. Okay, so taking all of that into account, that would mean a picture that looks like this. See this? This is called acetoxy. This is now in the interior of this C-looking thing. Right? This acetoxy group isn't here. It isn't here. It has to be here. Okay, so that's the diene hovering menacingly above the dienophile. The dienophile, I'm going to picture him here, but I'm going to tuck that electron withdrawing group under the diene, and I'm going to orient it in such a way that the electron donating group and the electron withdrawing group come out either 1, 2, or 1, 4. So that would mean that this is the proper orientation. There are my stars. There are my stars. There are my dots. There are my dots. And I see that the way I've drawn this, the electron withdrawing group and the electron donating group are going to come out 1, 2. Right, so that's the correct orientation. The incorrect orientation, or one of the many incorrect orientations that you could come up with, would be that, because this is going to give 1, 3. Okay, so now, time to draw the problem. Here are my stars. They now have a double bond in between. Here are my dots. They used to be bonded by a double bond, now it's a single bond. And on this carbon, I have a dash and a wedge. I have a dash and a wedge. Where is this acetoxy group? On the dash or the wedge? It's on the wedge. Okay, this carbon here, he also has a dash and a wedge. But the dienophile got tucked under. You see how I'm trying to draw the dienophile in the back there, showing how the how the pre-existing electron withdrawing group got tucked under. So that would be, I mean, it's not, there's a high, that's not the most beautiful picture in the world, but at least it communicates the stereochemistry and the regiochemistry of the reaction. How about let's clean this up? So I'm just taking this molecule and just straightening it out. Stars are over here. My acetoxy group is on a wedge, right? This hydrogen is on a dash, that's on a wedge as well. And this, I guess, I could draw that on the dash, like that. Okay, so this is the very same thing as this, I just straightened it up to communicate the pattern of dashing and wedging. Okay. Down here, I guess I also have a hydrogen. Let's get into that. Something like that. And so those two hydrogens are cis to each other in the problem. Okay, let's just try one more. How about so this is a self-Diels Alder reaction. I see the diene, right? The diene is trapped in that S-cis conformation, that C-looking thing, right? One of these molecules functions as the diene. The other one functions as the dienophile. Draw the structure of the problem. There's the diene, right? He's sitting on his little tabletop. There's that S-cis conformation. The other molecule of cyclopentadiene, that is going to contribute the dienophile. Maybe something like that. Okay, and so now this guy there's my new six-member ring. There's my new six-member ring. This guy got together with this guy. The dienophile got tucked under. So it would look something like that. And nothing happened to this double bond back here because he wasn't part of the reaction. So that would be kind of an ugly and hideous drawing of what the product would look like. Clean it up. Oh yeah, it's a way of making one of those witch's hat molecules. Right, there's a hydrogen here. There's a hydrogen here. They're both on wedges because the dienophile got tucked under. And then there's nothing happened to the double bond. Okay, so that's slightly better if kind of crammed in picture of what the product would look like. So any questions before we break?
I have a question about this specific problem.
Yes.
So does the third pi bond of the cyclopentadiene, when we're treating it as a dienophile, doesn't work as an electron withdrawing group? I was considering it more of an electron donating group, or does it not matter?
Well, it's actually an electron. It could go either way because it could have something that looks like this, right? Let's say there's the double bond that's involved in the reaction. Could do this. It could draw a resonance structure that looks like this. Yes? And so
Yep.
we see that the double bond that wasn't involved in the reaction was electron withdrawing. See where those arrows are headed?
Mhm.
Toward the double bond that didn't get involved. So you can interpret the second double bond as electron withdrawing. Is that what you're asking me?
Yeah, okay, thank you.
Okay, anything else before we break? Okay, well, I will wish you a good day, and I'll see you next time.